All right, welcome back. Now we'd like to look at NMOS device in inversion. Okay. So I'm not really going through the motions of drawing the band diagram. I'm simply showing you. But by now, I think you should be familiar. So if you want to get inversion, we need to apply a positive gate voltage. So VG is positive and large. Actually, it's not simple. We are actually going beyond inversion. We will discuss that in a moment. And large. Okay. And because of that, you have uh, first you have depletion of the semiconductor, and then we have inversion. Okay. So what happens? To understand this, let's try to first look at the bulk region. Let's say we have here there is phi f. Okay. Let's say this is basically Na equal to 10 power 17. Let's take this as an example. Per centimeter. Okay. So now if you change your concentration at the surface, okay. So I'll say the whole okay. So basically you can have, if you have the whole concentration, if this is P and I have my 10 power 17 at equilibrium, I should, okay. So if I go here, if I increase my whole concentration, I'm calling this as accumulation. Okay. And when I go lower than this, I'm calling it depletion. Okay. So once my EF at the surface, this is EF at the surface, right? If it crosses my EI, essentially the whole concentration is less than the intrinsic whole concentration, right? So what you have now is basically the Fermi level is closer to EC. Sorry, EC, yeah. So because of that, you have holes, okay? And we deplete, as we keep increasing the gate voltage. Suppose in this case, let's say, this is my gate voltage axis, VG. Initially 0, I'll be at flat band, right? This is 0 flat band. And then as I increase VG, I'll first reach depletion. This will be the depletion region. And after depletion, at some point, we are going to get into what is known as inversion. Okay, this switch is called as threshold voltage. Okay, what is this threshold voltage? To analyze that, first we will look at the surface potential. Okay. So the way we define threshold is in the case of an NMOS device, or rather number of inversion charges at surface is equal to number of majority carriers in bulk, by which we mean that, let's say in this case 10 power 17 is the number of holes in the bulk. Then we need to have 10 power 17 electrons at the interface. Okay, so here 10 power 17 electrons at interface. Okay. How do you know that? Well, I have carefully drawn this in such a way that this is my phi f, and even this is going to be my phi f. The distance is phi f again. Okay. So now what is the surface potential here? Psi s should be equal to EI. We'll take the EF as a reference level. So in the bulk, it is phi f minus, in the surface, it is actually minus EF, minus phi f. Okay, minus phi f equal to 2 phi f. So this is bulk, this is interface. Okay, so basically, whenever surface potential reaches 2 phi f, we say that there is inversion. Okay, we still have to relate surface potential to the gate voltage. We will do that in a moment. Before I go into that, I want to discuss the way the charges look like. Okay, so what happens is we are applying positive voltage. So there's going to be a positive charge on this side plus Q. And then what happens to the semiconductor, we have depleted it. So there's going to be some depletion charge minus Q. Okay. But as we increase the depletion, there is electron hole pair generation in the in the depletion region, right? So this is EHP generation in depletion region. This becomes significant after a point, right? If there is EHP generation, where will the charge go? Well, we will again redraw this just before inversion is reached. Let's say, what is the electric field? The electric field is going to be this and this, right? This is just before inversion. But once you reach inversion, essentially what we are saying is, let's say we cross the inversion, we have electron hole pairs generated. Electrons will come in this direction. Electrons will move here. N will go this direction. Holes will go into the bulk because electric field is in the plus X direction. Okay. So what happens is, whenever inversion is reached, you're going to have an additional charge at the interface. This is electrons at interface. Okay. The total now, once inversion is reached, okay, I don't have space. Let me create some space here by moving this up slightly. Yeah. So at inversion or in inversion, QG equal to Q depletion plus Q inversion. So in the semiconductor, there are two types of charges. One is the depletion charge, which is fixed. Okay. But electron hole pairs that are generated are free to move about. So electrons will come towards the interface. Okay. Just at the interface. It's a very, very thin layer of depletion, inversion charge. Okay. And because of that, this discontinuity will actually increase. If you look at this, we will give you this as an exercise. Okay, so look at this. If you look at E oxide divided by E of silicon, this will be greater than 3, much greater than 3 in inversion. Okay, we will give you this as an exercise. There will be a nanohub tool, and then I'll show you in the short demo at the end of this week. But you will also be able to run it and check it out for yourself. Okay? If you have inversion charge, this is how it will behave. So the inversion charge also is at the interface. You should not forget. You should remember that. Okay, and then the holes anyway will go into the bulk. How will the potential look like? If you are right at inversion, the potential is going to be simply again the same quadratic behavior. This is psi s. Sorry. And then there is a linear variation here. And the total is my Vg. Okay. So the voltage still falls always across the two oxide and the semiconductor. So this will help us actually derive what is the relation between the gate voltage and the size. Remember, we said at threshold psi s is 2 pi f. That's something that we can easily compute. But let's look at what is the exact relation. So what we are seeing is Vg is equal to oxide potential plus surface potential, right? So potential drop across the semiconductor. So this is simply going to be epsilon oxide, sorry, not epsilon, electric field across oxide times the oxide thickness. And by applying Gauss law, we know that this guy is going to be epsilon silicon, electric field in silicon divided by epsilon in oxide. Okay, so I'll make these substitutions, and I also know that this is basically QNA by epsilon silicon times the width of the depletion region. Okay, so I'll make these substitutions. I just showed a sequence of substitutions. So if you do all that, what you get is Vg equal to electric field oxide, so epsilon silicon, electric field in silicon, so that I'll write it as Q and A times W divided by epsilon oxide and epsilon silicon. So this will go, epsilon silicon will go. Oh, there's a T ox as well. There's a T ox we forgot. So this is basically going to be Q and A W by epsilon ox divided by T ox. Okay. Of course, plus psi s is always there. Plus psi s. Okay. This particular term is oxide capacitance. This term is Q depletion. Remember, when we have charge, we have the depletion charge here, right? The space charge. This was Na and this was W. So Q depletion will be Q and A W. Okay. And it's negative, so I'll just put a negative charge here. So the relation between gate voltage and surface potential is this. Vg equal to minus Q D, just to indicate that it's a depletion charge, by Cox. Cox plus psi s. Okay. So this is how the gate and the surface potential are related. So in the next class, we will do some problems and we'll try to analyze a little bit more depth. Okay. But before I close today, I just wanted to quickly talk about what happens in a PMOS device. Okay. So so far I have discussed only the NMOS device. So we have taken a P-type substrate, but in a PMOS device, we have to take an N-type substrate. Okay. You take an N-type substrate and then apply a positive voltage, then you will have accumulation. Okay. Vg greater than 0, you have accumulation. So please, take your time and then draw these diagrams by yourself. I didn't want to spend time drawing these again, so I'm showing you one shot, but you should definitely draw, okay, by yourself. You can try to use this as a reference, but try to do it by yourself and compare with the answer here. Okay. All right. So in your accumulation, when you apply a positive voltage, you have electrons accumulating at the interface. That's what we are showing here. This is electrons at interface. It's going to be the exact opposite of whatever we saw in the NMOS case, in a PMOS. This is plus Q, right? Gate charge. Now, if you deplete, you will have this exposed donors, okay, and minus Q in your gate voltage. So we have to apply Vg of less than 0 for a PMOS device. In NMOS device, we applied greater than 0. In PMOS device, we have to apply less than 0 so that we are depleting, we are pushing the electrons away from the interface. Okay. And then you continue increasing your gate voltage, you will reach inversion. So basically, one of the ways of representing depletion is basically when your surface potential is between 0 and 2 phi f. This we call it as depletion region. Depletion. The surface potential is greater than 2 phi f, or at 2 phi, greater than or equal to 2 phi f, we call it inversion. Okay. So in this picture, I'm representing just slightly above inversion. Okay. So in this case, what happens is you have this exposed donors, which are contributing a positive charge. This is your minus Q anyway. And you have an additional inversion charge at interface. Okay. How is this coming to the interface? Well, you have this depletion region which has been, out of equilibrium, right? We have removed all the majority carriers. So then the semiconductor tries to come back to equilibrium by generating electron hole pairs. When these electron hole pairs are generated, because the field is in the negative direction, right? This is the direction of field here. Holes will come towards the interface and electrons will go into the bulk. So that's why you have these holes, and that is why we call it the PMOS device. So PMOS device implies holes are inversion charges. NMOS device implies electrons for inversion charges. Okay, that's the name. That's why whenever we want to talk of PMOS device, we take an N-type substrate and invert it. That means we convert N-type. You should have ideally electrons there, but then we deplete it and then we make it have holes. We are switching it. We are inverting the semiconductor. That's why we have holes as inversion charges. And in a this is in a PMOS device. In an NMOS device, electrons will be the inversion charges. So that's why we start with the P-type substrate. Okay. So I hope this is clear to you. This is not a simple thing. I mean, this is something that I remember when I first learned it. It looked like I learned it, I understood. But then when I look at it after a couple of years, I realized that I have not fully understood it. Okay, it takes some time for you to understand. So please go through it a couple of times, understand the physical mechanism. So all these diagrams might look like a lot of shapes, a lot of variations, but they're all very simple to draw if you go towards it in a logical way that I have been using. Just go step by step, and all of this will be clear. Okay, and we will try to solve some problems in the next class, and we'll also relax certain assumptions that we made for an ideal mass capacitor. Okay, and so yeah, we'll do that in the next class. Thank you so much for your attention, and I'll see you in the next lecture. Bye.